Hey, what's up, chemistry people? Mr. Boylan here, and today we're going to start our new unit on kinetics. Today we are going to explain specifically how reaction rates that depend on temperature and other environmental factors are determined by measuring changes in concentration of reactants or products over time. As always, we're going to break that down a little bit to make it a little easier for us. First thing we're going to do is define rate. And this unit on kinetics is all about rates and how fast or how slow chemical reactions proceed. We're then going to describe factors such as temperature, concentration, and surface area that influence the rate of reaction. So how do those things either speed up or slow down a chemical reaction? And then lastly, we're going to analyze some concentration versus time data to determine what's called the rate law for a zeroth, first, or second order reaction. And we'll talk about what those means in terms of what's going on with the rate or the speed of the reaction. But again, it's going to come down to analyzing what's going on with the concentration versus time data. Okay, so first things, what is a rate? I'm confident that we have heard rates in other contexts, but a rate of a chemical reaction is just a measure of the change in concentrations of reactants or products over the change in time. Essentially, how fast or how slow is a chemical reaction going to proceed? Now we can measure the reaction rate as the decrease of the reactant concentration per unit time, or we can measure it as the increase of the product concentration per unit time. Regardless of whether we are measuring the changes in reactant concentration or product concentrations, we can then determine what's called the instantaneous rate simply by, again, measuring those changes in concentrations over the changes in time. And as you look at your screen, there are a couple ways that we can express that instantaneous rate, again, just depending on whether we're talking about reactants or products. Importantly, though, you'll see several different units for the rate. Molarity, concentration over your unit of time, whether that's seconds, minutes, hours, days, years, whatever we're talking about. Molarity, T to the -1, same thing. Or you'll see moles per liter per unit time. Again, the moles per liter there is your molarity, just spelled out for you. Or moles per liter per time, per unit time, again with the little superscripts of -1. All of these are the exact same thing, concentration unit per time unit. But it is important to recognize that the rate is not constant. As the reactants are consumed or your products are formed, the rate decreases. And again, this is because we're using up those reactants, and so there's not going to be as many reactants around to interact with the other reactants to form your products, and so the rate's going to slow down. And the last thing to keep in mind here as we think about rate is that we're going to use what's called Beer's law to determine the concentration of colored solutions as the reaction proceeds. But for right now, just be aware of that name, Beer's law, and recognize that it is going to be something that we use in the kinetics unit when we're trying to determine the rates of reaction. Okay, so now that we've sort of defined what rate is, let's talk about some things that will affect the rate. One, increasing the surface area of a solid reactant can increase the rate by increasing the number of collisions between the reactant particles. Two, you can add what's called a catalyst to increase the rate of the reaction by lowering the activation energy of a reaction. And we'll talk a little bit more about that in a couple of days. You can also increase the temperature, which results in a faster reaction. The rate speeds up. As we'll learn, the rate constant is temperature dependent, and a rise in temperature will increase the rate constant, essentially heat them up, speed them up. There's going to be a greater number of interactions of your reactant molecules, and therefore your rate will increase. And the fourth thing is increasing the concentration of your reactants will increase the amount of reactants essentially colliding with one another, thus yielding more product. So increasing concentration will increase the rate of your reaction as well. All right, so the next thing we're going to talk about here is essentially how the rate of reaction sort of depends on the concentrations of your reactants that you're working with. And so as you take a look at sort of the general formula that you're given there, the rate law or the rate of reaction can be expressed as you see there. We've got the rate constant K times the product concentration of your first reactant times the product concentration of your second reactant raised to these exponents x and y. Again, k represents the rate constant. X and y then are described as the orders with respect to A and B respectively, but note they're not necessarily the stoichiometric coefficients of A and B. Bottom line, these orders are going to tell us what effect the concentration of that given reactant has on the overall reaction. And generally speaking, the larger those orders are, so the larger those exponents are, the greater the effect on the rate of the reaction, which makes sense. Okay, so what would this look like in a sample equation? As you take a look at the decomposition of hydrogen peroxide here into water and oxygen gas, you see the rate law, or the rate of reaction provided to you here, where you've got that rate constant times the concentration of the reactant, in this case hydrogen peroxide. What we say, or what you're going to start seeing here, is you'll hear it read as the reaction is first order with respect to the reactant H2O2, since the concentration of H2O2 is raised to the power of 1 in your rate equation, or in the rate law. So what are these orders exactly? What do they mean? Well, you can have a zero order rate reaction. In other words, the rate of the reaction is independent of the concentration of the reactants. And as you look at your rate law for that, you'll have your rate constant times the concentration of your reactant to the zero power, or I would say that's zero order reaction. And because anything to the zero power is 1, you'll see zero order rate reactions, or zero order rate laws, written as rate equal to k. But you can also see it written like this. Just recognize anything to the zero power is 1. First order rate reactions, or first order rate laws, are described as such because the rate of the reaction is directly proportional to the concentration of one of the reactants. Sometimes the one is omitted, so just keep that in mind. We often will drop that. And it's important to note that radioactive decay is one of those reactions that's a very common example of a first order process. They have a constant half-life, meaning the time taken for half of the atom's decay is constant and independent of the initial concentration. And for these types of reactions, there is an equation that's on your formula chart for first order reactions, for the half-life of first order reactions, which is provided to you there. Our second order rate reaction, or our second order rate law, is described simply as where the rate of the reaction is directly proportional to the square of the concentration of one of the reactants. And again, you see that expressed in your rate law, your rate equation there. But where do those numbers come from? How do we know if it's zero order, if it's first order, if it's second order in regards to any one of those reactants? You may think that it is something as easy as pulling the stoichiometric coefficients from the balanced chemical equation like we did for the instantaneous rate, but that is not the case here. When you're writing the rate law, you have to pull that information from experimental data. The only way to determine the order in respect to one of the reactants is to do an experiment and see what happens when you change the concentration of that reactant. So as you take a look at your notes there, you're given a sample reaction and some sample data that was collected from several trials of that reaction as the concentrations of the different reactants were varied. Now, what you want to do as you're trying to figure out what the orders are is to pick a couple of trials in which one of the reactants stays the same, so you can easily determine how the change in concentration of a single reactant affects the rate of the reaction overall. Okay, so as we take a look at our data here, and we are again trying to find a couple of trials in which the concentration of one of the reactants is held constant, we look at trials 1 and 2. Here, the concentration of our chlorine reactant is held constant between those two trials. However, our reactant of NO is doubled. So we go from 0.2 molar to 0.4 molar. Now, by doubling that reactant, note what happens to our reaction rate. It increases by a factor of 4. meaning that the rate of this reaction with respect to NO is second order. In other words, when we double this, the rate quadrupled. And so we would then describe the rate of the reaction with respect to NO as second order, because as this doubles, the rate quadruples. And second order is simply defined as directly proportional to the square relationship of one of your reactants. As you scan your data for a couple of trials now in which the other reactant is held constant, so in this case the concentration of NO is held constant in trials 1 and 3, note what happens to the concentration of our chlorine. It doubles here between 1 and 3, and note that our rate doubles. So we would say that the rate of reaction with respect to chlorine is first order. And when we say first order, we simply mean that the rate is directly proportional to the concentration of one of those reactants. Now, when you want to figure out what the order is overall for the reaction, all you have to do is simply sum together the individual orders of each of the individual reactants. So in this example, because the reaction was second order in respect to the NO and first order in respect to the chlorine gas, the sum of those two, 2 plus 1, is going to be 3. So this is third order overall. Okay, now a last but important concept here to think about is how we can use graphs to find the overall order of the reactions. But keep in mind that these plots are going to use what are called the integrated rate laws, which we'll talk about in just a minute. But bottom line here, we're looking for some plots that will allow us to predict or estimate essentially what the concentration will be at a future time, which does more for us than when we were looking at just the instantaneous rate or at the at a single point in time. And so you want to commit these to memory, that if you plot concentration versus time and you get a straight line, you get a linear relationship, that is indicative of a zero order reaction. If, on the other hand, you get a linear relationship when you plot the natural log of the concentration versus time, we say that is indicative of a first order reaction. If you determine that you get a linear relationship when you plot 1 over the concentration versus time, that's indicative of a second order reaction. And we'll talk about that in just a couple minutes. We'll look more at that at the lab. But basically here are just a couple things to sort of organize in your mind. There are what are called the differential rate laws, which are commonly just called the rate laws, which show how the rate of the reaction depends on concentration. And that's where we were doing earlier with the zero order, first order, second order, etc. But we also have what are called the integrated rate laws, which show us how the concentrations of the species in the reaction depend on time. Now, this is super helpful for us if, again, we want to know what's going to happen in some future point. So in general, integrated rate laws are used to determine the concentration after a certain time has passed. That's more helpful to us than just to determine the rate at some instantaneous point. Now, I don't want you to freak out about having to integrate your differential rate laws unless you are a calculus boss, which I know some of you are and can probably do it no problem. Just recognize that integrated rate laws are provided on your formula chart for you. All right, so the majority of your video today can be summed up in this one table. Okay, so just a couple of things to sort of take away from this table, and let's take a look at zero order reactions first. As you take a look at this data table, again, you're provided with the order of the reaction here. This is your differential rate law, or oftentimes it's called the rate law. These are your units here. We'll talk about how you can solve for those pretty easily for your rate constant K. And then the integrated rate law is provided to you here. Now notice it's in the y equals mx plus b formula. And so again, basically we're just going to use the integrated rate law to figure out, if we know the initial concentration of our reactant, then at time t, what will the concentration of the reactant be? And that's really what we're using the integrated rate laws for. And again, I don't want you to be scared away by the calculus here, or how you go from your differential rate law to the integrated rate law. You'll be given this information on a formula